Hello? Hello? Do these work? Hi, guys. Welcome, welcome. It's really nice to see a lot of you. It's nice to see all of you. Sorry, not a lot of you. Yeah, so you're here for the second Zero Knowledge Summit. This has been a pretty exciting road getting to this point. There's a lot of people who applied to be here. I've had to say no to a lot of people. You are the lucky few. Welcome. So, I'm Anna.
I'm Frederick.
And we're the co-hosts of a podcast called
Wi-Fi info first.
Zero Knowledge. So yeah, the Zero Knowledge podcast, I think some of you might know about it. We're going to tell you a little bit more about it as we go on. To start though, I'm going to share just some practical info. Why is this?
Oh, maybe
there.
It is bottom.
That's this way. So, practical info. First piece of practical info is, I really like this color scheme. It's extremely bright. I don't know why, but this is where we're going with it. I hope you don't mind. It might make your eyes burn just a little bit. All right. So Wi-Fi, there are signs around the room to get hooked up to the Wi-Fi. Please do that. There is a Telegram group, which you should have received an invite to. Try to get into it. Oh, wait, what? What did you need? This guy? Sure. So breakout, use this group to just let people know what you're doing. I think it would be really cool. Yeah, amenities. There's coffee all day. There's going to be some lunch. There's going to be some drinks later. Everything should be taken care of. I think if you try to buy... this podcast in
2018.
Alibaba Cave for fun and profit. It's like saying I know how to sing, but I don't have to sing to you. This is a good one. Look at it closely. It's slightly murdery. I don't. That's fair too. This is a thought. This is a bit of a longer one. I like the creepy assumptions in that. Nice. This was a few of them too. Even though I have a vague idea, I would fumble at the explanation, get blank stares, and then it's hoping this conference helps me with it, and we hope that as well. Cool, so I think what we want to do now is just say thank you to some of the people who helped make this happen. This edition is our main sponsor is Decrypt Capital. This has been a very cool partnership. They are focused on, they're an investment firm focused on privacy preserving technologies, and we just felt like this was such a cool connection point, and I really want to say thank you to Decrypt Capital for coming on board. Our gold sponsors are NewsCipher and Least Authority. So zkSNARKs is a data layer for blockchains and decentralized applications that gives developers a way to store, share, and manage private data. And Least Authority is a Berlin-based company that supports people's rights to privacy through security consulting and building secure solutions. And actually, it was a so zkSNARKs was here last time. I know their session was super popular last time, so I'm so glad you guys are back. And Liz from Least Authority sort of helped, I mean, the framing of this event came a little bit through conversations that we had. So I don't know if Liz is already here, but anyway, it was really great that we had those conversations. Do you want to share the other ones?
Well, we also have a bunch of other great sponsors, and obviously we want to thank everyone from Parity, POA Network, 1KX, Zcash, and the VPN Private Internet Access, who decided to sponsor us as well.
I want to say a shout out to the team who's kind of come together in the last few days around this event, and a big thanks to Lorenzo, who's dealt with a lot of my being late to things, and like he's helped me get organized, so I want to say thanks to him for that. And thanks to you. And thanks to you.
For the record, Anna has done most of the work for this conference. I'm really just here being a pretty face.
Yeah, back to the program. I think what we can do right now is basically just show what's coming up right after this. We're about 2 minutes late, so I think we're not too bad. But we're going to start with Ariel Gabizon from Zcash's talk here on the main stage about Zcash and zk-SNARKs. There's an identity roundtable starting in breakout 1, run by Garrett and Paul. And then Awa is going to be doing something on proof of stake in the sidechain stage 3, which is all the way at the end of the hall. So yeah, I hope you guys choose what you want to watch. And just once again, this is the Wi-Fi. So you didn't have to take a picture. I was going to show it again. Anyway, yeah. So thank you guys so much. And I'd like to welcome our first speaker, Ariel. Ariel. No, I said it wrong.
It's like don't think about
it's like a thing. If I do it, something tells me I do it.
I need the where's the HDMI? Two out of three. Okay. Okay, thanks. Just see how this works. Okay, it works. Okay, so this is going to be an introduction, but you know, kind of maybe adapted to the crowd here. So I'm going to try to give some intuitions about how the Zcash protocol works and how SNARKs work. Okay, so the Zcash protocol. Let's go for a second to Bitcoin and think of it through the following analogy. So right, the main object there is the unspent transaction output set. And you can think of that as some bowl that everybody can see what's in the bowl. And this bowl contains everybody's unspent coins. And what is a coin, right? A coin is like an address and a value. And let's assume for simplicity that all coins are $1. Right, so at some given point in time, these are the current unspent coins. Alice has 2, Bob has 2. And so how does payment happen in Bitcoin when you're thinking about it like this? Alice wants to pay Bob, so she creates like a new Bob coin. She puts it inside the bowl, and at the same time, she takes out an Alice coin. And the idea is that since everybody's looking at the bull, everybody can see that, yeah, she really took out one of her coins and she put in what she took out, so everything is fine. But of course, you have there's no privacy in such a system at all because everybody is looking at this bull. So in Zcash, you can think of it that we replace this bull by an opaque box. So you can't see into the box. This is just for the presentation. And think of this box as having a small opening on the top. So this is a box that you can drop things into, but you can't take anything out once it's in, and you can't look inside. So and also think that we've added to each coin some random serial number. We've chosen some random number and added it to the coin. But think of all these coins still as $1 coins. So the big difference so far from Bitcoin, one big difference is that once something's inside the box, you can't take it out, and of course you can't look into the box. All right, so we need some way to distinguish between spent coins and unspent coins, right? So we're going to add next to this box a list. This list, everybody can see the list. And what does this list contain? It contains the serial numbers of all coins that have been spent up to this point. So say at a certain point in time, out of these 5 coins, only this coin of Alice was spent. So this list will contain just this number, 421. And right, this serial number, it's just a random number. It doesn't give you the ID of the coin holder. Okay, now the question is, so how does Alice pay Bob in such a system? So like in Bitcoin, she's just going to create a Bob coin, and she wants to now drop it in the box. But before she drops it into the box, we ask Alice to write a new number on the list, a number that's different from what's on the list so far. And what is this number Alice is writing on the list? It's a serial number of some coin of hers that's still unspent. So, for example, if Alice is going to use this coin to make this payment now, she's going to add this serial number to the list. All right, so basically the idea is, instead of preventing double spending by taking spent coins out of the bowl, we prevent double spending by requiring unique numbers on this list. But of course, at this point, this could all be nonsense, because we don't see into this box. So how do I know that this number that Alice is writing on the list is not some completely random made-up number that doesn't have anything to do with anything? And as you can guess, the answer in 2 words is zk-SNARKs. So Alice will somehow use zk-SNARKs to prove that this number she's writing now on the list is really a serial number appearing on some coin in the box, a coin that says Alice. So that's the Zcash protocol in 3-4 minutes. And now I want to give you some intuitions about zk-SNARKs. So I like the most, this is a kind of advanced definition of SNARKs I heard Zuko Wilcox give, that a SNARK is a bunch of words scientists put together, so their initials will spell SNARK. It's an advanced crowd, so I can use that definition. It corresponds very closely to something Silvio Micali called computationally sound proofs somewhere in the beginning of the 90s, but SNARK is more tweetable and retweetable than computationally sound proofs. So I want to give you some intuition about what I see as the two main ingredients in making a SNARK. And the first ingredient is that we're going to move our statement to the world of polynomials. Why are we going to do that? Because basically, if you tell a lie in polynomials, you need to lie most of the time. And just as a historical anecdote, this kind of idea, it appeared first in a really great breakthrough work that what this work allowed us to do is say there's a Sudoku puzzle that there's no solution to, and I want to efficiently prove to you there's no solution to this Sudoku puzzle, right? Forget zero knowledge for a second. If I wanted to prove to you there is a solution, I would show you the solution. Say I want to prove to you there's no solution, I want to do it quickly without you having to go through all the possibilities. So this classical work of Lund, Fortnow, Carl Finissan allowed to efficiently prove what's called co-NP statements of the form, for example, there is no solution to this Sudoku puzzle. So if you tell a lie in polynomials, you need to lie most of the time. Let's give a concrete example of what I mean by this. So say, for example, the lie you wanted to tell was, this program here that I starts from 0, and 10 times we increase I by 1. I want to tell you the lie that this program outputs 11. So now I'm telling you, I want to tell you the story of how this program ends up outputting 11. So I tell you the story of its execution, of how the state changed, how the value of I changed. And, I tell you the story, well, I was 0, and then we had this plus plus command, so the state of I became 1. And then again, we had another plus plus command, the value of I became 2. I continue, you're getting bored, you see I'm not lying, it's just some formality. And then when I see you're a little, a little bored and not listening, and I say, and then suddenly at this, there was a point where I was 6, and then, there was the plus plus command, I became 8. I slip that through you, and then you wake up a little, and then I continue not lying, and then, I was 8, there was a plus plus command, it became 9. So the point is, when we're talking about program executions, if I slipping in one lie is enough to successfully make a completely false statement. I only need to lie in one place to get a completely wrong conclusion. Okay, but now the idea, and this is kind of the basic important idea in SNARKs, the first of them, is suppose I tell you now, all right, tell me the story of this program executions, but tell it to me as a polynomial. What does that mean, tell it to me as a polynomial? I'm saying, well, so what is this story? I can think of it as 10 numbers, right? The 10 changes in the state of I, in the value of I. So, you know, I have 10 values, you know, what's called Lagrange interpolation. There's some degree, at most 9, polynomial that gets these 10 values, that at these 10 time points will output these values. So I tell you, you know, find this polynomial and, you know, tell me its values. But, you know, do me a favor, you know, tell me its values not on these, just these 10 points that correspond, you know, to the program execution. If you've already found this polynomial, you know, just write to me what its values are also on, you know, on other points. And you could say, why, the value of this polynomial on other points, what does that have to do with the program? Well, just do me a favor and write them for me. And you say, okay, so say you weren't lying. So what is, right, what is the true story? I always changes by 1 at any time point. So I need a function that x equals 1 gives me 1, x equals 2 gives 2, x equals 3 equals 3. What's the degree at most 9 polynomial that gets these values? It's not too hard, it's just the polynomial, the constant 1 that always returns 1. And how does this polynomial behave on the numbers 11, 12? What is f of x, f of 11, f of 12, f of 13? It's just 1. So if I'm not lying, this is what I will give you. But now the important point is that say I am lying, and just at this one point, you know, that I wanted to falsely claim that at this one point I grew by 2 instead of 1. So the point is that now my lie will manifest a lot very clearly. So now I need to find a degree 9 polynomial that gets these weird values, 1, 1, 1, 1, 1, then suddenly 2, and then 3 more 1s. So you do what's called Lagrange interpolation. You find such a polynomial. This is just an approximation. It's going to look something like this, 0.00 something times x to the 9th. And again, on the points 1 to 10, it's very close to the true thing. But the point is that now outside this range, you know, the lie is going to become very clear. The values of this polynomial are going to be very, very, very different than the correct one. So the point, again, with polynomials, in other words, is that once I force you to tell me a story in polynomials, if you want to check that I'm lying, it's enough to check basically at a few random points, or even one random point. Because my lie, when I'm telling the story in polynomials, will manifest almost everywhere. All right, so that's, and the second main ingredient in SNARKs is what we can call homomorphically hidden verifier challenges. And before saying what I mean by that, let me say what I mean by a homomorphic hiding. So this is a term I kind of thought of, but then I saw that in the crypto literature it corresponds very closely to these things called k-linear maps and graded encoding schemes. And this is very similar to homomorphic encryption, which I'm sure you've heard the term. So what does a homomorphic hiding mean? Well, it's some mapping E that it has two main properties. So one property is that if I show you E of X, it's hard to find X from that. So that's what hiding means, right? If I show you E of x, it's hard to compute x. The reason I call it hiding and not encryption is that there's no decryption key. There's not necessarily a way to get, even if you have some, there's no key that lets you get from E to x back to x. That's why I call it hiding instead of encryption. So that's the hiding part. What is the homomorphic part? The homomorphic part, what does that mean? It means that if I say give you a hiding of x and a hiding of y, well, it's a hiding. You can't get x or y, but you can get other hidings of arithmetic expressions in x and y. So for example, I give you the hiding of x and y, you'll be able to compute the hiding of x plus y and the hiding of x times y. Small note, I'm simplifying. You can't actually get anything like this. We don't know, so it's going to be some E prime here instead of E. All right, so that's basically the idea of homomorphic hiding. Now, how does this, and the idea in our context, what this allows you to do is this thing called blind polynomial evaluation. What does that mean? It means, say that the prover has some polynomial, right? So let's think, where were we at? We were at this stage where we know, okay, if I force the prover to tell me the story in polynomials, it's enough for me to check him at one random point. But there's a little chicken and egg problem here of who goes first. Because if I say to the prover, okay, I'm going to check you at x equals 13, what's your polynomial? The prover can craft a lie that looks good on x equals 13. On the other hand, if the prover goes first, he said, okay, I'm sending you all my polynomial. We got two problems with that. One problem is, right, SNARKs, the S stands for succinct. We want small proofs. These polynomials of the prover, they're going to be huge. And the second problem is we'll lose zero knowledge. For example, in Zcash, the prover polynomial, it contains all the information on the addresses, the values of the transaction. And so the kind of the clever way people figured out how to solve this chicken and egg problem is, okay, the verifier in a sense will go first. He'll give the challenge point first, but he won't give it in plain form. He'll give it in this homomorphically hidden form. And what does that do? That, I'm glossing over a lot of details, but basically that creates a situation where, on the one hand, since it's hidden, the prover can't adapt their answer to the challenge. They can't choose a polynomial that will work well on the specific point of the verifier because it's hidden. But on the other hand, since it's homomorphically hidden, the prover can still, if his polynomial is P, can still compute the hiding of P of S, just where S is the challenge point, just from the hiding of S and some hidings of powers of S to be completely, to be more accurate. How is the time situation? I got basically one more slide. I'm good, all right. It's actually a trick if you want speakers to go fast. Don't show them how much time is left because they'll assume there's, well, maybe it depends on the speaker. But I'm guessing it made me go a little faster. So that's the basic idea, and I want to tell you one more thing about, people call SNARKs moon math. So where's exactly the moon in the moon math? And in my opinion, the real magic is in these things called elliptic curve pairings, which were, developed by mathematicians who didn't probably know or care about cryptography. They cared about like the Riemann hypothesis and proving things about prime numbers. And so elliptic curve pairings are where a lot of the math magic happens. This pairing, it gives you this thing. You have two groups, G and what's called the target GT. And the discrete log is hard in these groups. So if I show you G to the X, you can't find X. I show you G to the Y, you can't find Y. But this pair of groups, these groups, they have this magical property that you could say partially contradicts the classic Diffie-Hellman protocol. So basically, this pairing map, what does it allow me to do? If you give me G to the X and G to the Y, I can compute from that. I can't compute exactly G to the X times Y, right? That would like totally contradict computational Diffie-Hellman. But I can, in this other group, what's called the target group of the pairing, in that group, I can efficiently compute xy to the exponent. So for some generator of this group, from these two guys, I can actually compute h to the x times y. Okay, so I think I'll just open, any questions about, by the way, anything Zcash related or not just the talk? Okay, yeah?
What exactly, so we had the Zcash example.
Yeah.
Drawing the Bob coin.
Yeah, let me go back.
Is the fact that it's Bob's coin hidden as well? So what is with throwing of that coin? What about it is also not known? Can you repeat the question?
All right, so in this example where Alice is paying Bob, how hidden or what is hidden about Bob's coin? So the sender, like Alice, will know the value of the coin and the address of the coin, like she'll know it's Bob. But this serial number, like the way I did it here, so for example, Alice does know, she made this coin, so she does know the serial number, the 627, and when Bob spends it and writes 627, Alice will know Bob spent her coin. In the real Zcash protocol, only Bob knows this 627, because this 627, it's actually going to be some combination of Bob's secret key and the coin.
So how do I prove that the coin with the serial number is on the list? Like what proof, ZK proof do we produce?
Okay, so what you have actually is, so you have, you publish, when I create the Bob coin, I publish the hash of the coin, or a commitment to the hash of the coin, and everybody stores this Merkle tree whose leaves are the hashes of the coins. And also, this list is public. So Alice will prove, when Alice spends this coin, she will prove I know some, coin, such that if I, and some path in the tree, such that if I take the hash of this coin that I know, and I follow this path of hashes, I will reach this root that we all agree is the root of the tree of all the coin commitments. And at the same time, Alice will prove this. And she will also prove, and this coin that I know a path to the root, the serial number, or as we call it, nullifier of this coin, is what I wrote on this list.
So does that mean that the entire Merkle tree is an input to the ZK function?
No, so just the root of the Merkle tree. So the root of the Merkle tree is what's called a public input to the circuit, and the path from your specific coin is a private input to the circuit.
Any other questions?
Hi there. So, just going back to that example when Alice is sending a zero-knowledge proof that she owns a coin that is part of the Merkle tree. How does she create Bob's coin if she doesn't know what the nullifier is because she doesn't know the secrets?
So, the nullifier, or what I called your serial number, let's call it nullifier, is a hash, basically, of the coin that Alice does know, and Bob's secret key. So Alice doesn't know Bob's coin, Bob's nullifier, but she doesn't need to know it. It's only important that when Bob spends the coin, he will know the nullifier because he will need to publish it and prove that it's correct. But an important point here is that when Alice creates Bob's coin, she doesn't actually need to know the nullifier. All she needs to convince us is that the value of, she doesn't need to know the value of the coin, and that's all. She just needs to convince us that the value of this coin that I've dropped is not larger than the value of the coin I've added to the list.
Yeah, sorry, I'm a bit slow, just off the plane.
Sure.
Deprived. But does that mean that, does Bob need to give Alice a bit of information in order to make that coin?
Just his address. The coin is basically address, value, and some randomness that Alice chose to make the hash of the coin more random.
Okay. I think I understand. Cool, thanks.
We have time for one more question, if there is one.
I think you got over there.
You mentioned something interesting, that coins can have different values, and then you can spend a coin with, like, you can transfer it to another coin with lesser value.
Yeah.
Is this exact protocol of Zcash?
Yeah, so in the actual protocol, I can add a few numbers to this list in a transaction, and I can drop a few coins to the box, and then in the circuit, I check that the total value of coins I've added to the list is larger or equal to the total value of coins I dropped in the box.
Is this larger equal actually used to hide the value transfers? Because otherwise I could track, like, if somebody spends exact same amount of coins, like I could try to build an algorithm to track the origins of the funds. Is this used or not?
Oh, sorry, I think I said larger or equal for simplicity. I think it's actually that's a good idea, maybe to use that for some extra hiding. But I think I should double check. I think it's actually exactly equal, and everything else like goes into the transparent pool if there's any change.
All right, thank you very much. Let's give Ariel a big round of applause.
Thanks.
Presenting ZoKrates.
Okay. No, I don't know. How do I do it? Microphone. That's what's
Hi everyone. I'm Thibaut Schaeffer. Today I'm going to be talking about ZoKrates. So giving kind of a general introduction for those of you who are not familiar with the tool, and also kind of talk about some of the concepts and ideas we've been working on recently. Again, yeah, check out the episode that's going to come out soon with Zero Knowledge Podcast. That should be a good one. So before I start, I should mention ZoKrates was started at TU Berlin, and we're proud to have had the support of the Ethereum Foundation since the start. So with that out of the way, let's jump right into it. So one way we like to think about it is that in the blockchain space, since Bitcoin, we've basically seen two main trends. One trend is towards more generality with Ethereum and smart contracts, and everyone can write whatever they want, and you have all this freedom. And privacy on the other side with Zcash, with kind of more private systems. What we think at ZoKrates is that by combining those two aspects, we're likely to bring more innovation into the space and to let developers come up with the actual interesting use cases. So we really want to be up there on the right on this graph. However, if you look at Zcash, there's amazing systems being built at Zcash. However, for the average developer, it's still really, really hard to get started with zero-knowledge proofs because the abstractions are being used are very, very low level and very close to what you would be doing with an actual circuit board where actually you would want something a little bit more high level and developer friendly to get started. So we want to enable developers to write privacy-preserving applications, and maybe I can kind of give a quick overview of what that could be, even though, of course, the use cases will be found by the developers eventually. So in general, approving facts on private data is something that you can do with those systems. In particular, approving membership in a Merkle tree, shielded token schemes, schemes such as the Zcash scheme as well, commitment schemes, and finally maybe another type of use case that we're also looking at, which is not directly linked to privacy itself, but it's compression. So taking, for example, a number of proofs that were generated like normal using other tools, and kind of take those proofs at input and then compress them to have one single succinct proof that kind of sums up all those proofs as input. And we have some projects who are using ZoKrates to do that. For more on the applications, we have a panel this afternoon that will go more into what people are actually building with those systems. Given all those applications, the space, especially the Ethereum community, thought, oh, that would be great to be able to use those tools. However, they require some cryptographic primitives that are quite specific. And for those familiar with Ethereum, on Ethereum you can only use this EVM, the virtual machine, and actually implementing those primitives on the EVM was really, really costly in terms of gas. So last September, last year, there was a hard fork in Ethereum, which introduced basically three new primitives in the form of precompiles, what we call precompiles, which are basically primitives that you can call from the EVM, but that can be much more complex and for which you pay just a fraction of the cost because they're not executed on the virtual machine itself, but they're executed natively on the host. So you kind of have a huge savings on that. And those primitives were elliptic curve operations on LBN, which is the curve that's currently used in Zcash. So including pairing checks. And pairing checks are known for being kind of the underlying cryptographic tool necessary to use the current zero-knowledge systems, such as the one used by Zcash. So that was added into Ethereum, making it possible for anyone to go and start doing zero-knowledge proofs on Ethereum. However, that did not really happen because they were just introduced as this very, very low-level primitive, but there was no way anyone could actually take that and actually build something on top because it was so low level. You didn't even have the proving system. You just had this very kind of basic primitive. So yeah, here's some tools. Go and use them. It's actually not that easy. So that's where ZoKrates comes in. And what we actually built is a domain-specific language where you can define your computation, your privacy-preserving computation. So Ariel talked about like public inputs and private inputs. That's something you can define directly in the ZoKrates program. So here we have the main function, and the main function has inputs. The first input is private, which means that when you're going to generate proofs, this value A will not be revealed, and has also public inputs, so the value H will be revealed. And in this case, what we're doing in this program is proving that we know the preimage of a given hash. So you kind of feed your secret preimage A, and you feed the public hash H, and then you basically return 1 if the hash of A is equal to the public hash. And then you have some hash function that you can define in ZoKrates as well, and so on. So trying to have this very like high-level abstraction for people to build on. So what it looks like in general is a whole pipeline of tools. So starting from the domain-specific language, we have tools to actually run a setup phase, similar to the one run in Zcash, which generates 2 different things. One thing is a prover. And the prover is basically a piece of software that will be run, let's say, on the client of the prover, or whoever wants to use the application. So in Zcash, that could be someone wanting to spend some coins. And that's something that's completely independent from any blockchain. It's just a piece of software that lets you generate proofs. And the other piece of software that we generate in the other target is a verifier, typically. And what we built is that our verifier is actually a piece of Solidity code that you can deploy directly to a blockchain, so that end-to-end you could have someone generating a proof on the client, for example, proving that they are above 18, and then sending this proof to a smart contract, and the smart contract could just take this proof and say, okay, this is valid, and do some access control based on that. So this is a kind of use case that we're looking at currently. So great, we have this tool, we have this high-level language, so we can start writing all our programs in it, and everything will be fine. So that's basically what we did. So we wrote, as seen in the previous example, we implemented a hash function. Especially the SHA-256 compression function, so just 1 round of SHA-256. And here's how it went. So as you can see, our implementation has, our kind of naive implementation has 250,000 constraints. And in the case of those systems, the more constraints you have, the less efficient your system is. Because if you have a lot of constraints, it's going to take a lot of time for the prover to generate the proof, and for the setup as well to be executed. Whereas LibSNARK gadgets, which is the kind of library that most developers use currently, has an implementation of SHA-256 in just 27,000 constraints. So of course, our implementation is very naive, and we could have more optimizations, but our approach is to say, oh, we have this great implementation already, why not just try and kind of import that into ZoKrates and see how we can kind of interoperate between those 2. So our goal is going to be to find kind of a common language between those 2 tools, kind of ZoKrates and other tools such as LibSNARK. So we looked at what good candidates we could have for this kind of interoperability between the different tools. And you can see it as ZoKrates and the LibSNARK gadgets kind of standing on top of this common abstraction, which is basically arithmetic circuits. And arithmetic circuits can be represented in this form called R1CS, or rank 1 constraint systems, which is actually pretty simple. It's just a list of so-called constraints, and each constraint is sort of an equation like this, where you can have one multiplication, so here W times this kind of product, and so only one, let's say, on the left, and no multiplication on the right. And then the elements that you multiply need to be only linear combinations, so like a sum of factors of your variables, right? So you, in terms of arithmetic circuits, you can think of it as a circuit that has plus gates and multiplication gates. And in this case, what each variable is, it's a variable that lives in a prime field, which is basically a field that has, whose size is a prime, a very big prime, right? So this is a very simple abstraction, and it's a, okay, let's use that. We'll just take the zk-SNARK gadget, just compile it to R1CS, take that, feed it into ZoKrates, and there we go. We have our 27,000 constraint hash function. So when we did our implementation of SHA-256, we were basically very close to R1CS, saying, okay, we create a first constraint, and we set some of the values, some of the variables to some values, and then in the next constraint, we can reuse some of the variables and say, okay, this is another constraint, and then by going through all the constraints, you can find a solution to the system, right? So just looking at R1CS, you can actually write complete programs. However, if we look at something that we would want to do, which is turning a number into its bit representation, and that's something that's really useful, especially in the case of SHA-256, because SHA-256 is based on bits. So you absolutely need to have a way to kind of represent bits to implement this algorithm. And it turns out that if you want to take a number, which is living in this kind of prime field, so it's just like an integer, and you want from that to output the bits that represent this number, and imagine you only have this abstraction that we had before, which is just a bunch of constraints that are just multiplication and additions. Actually, it's going to be really, really hard if you just have those tools to go from a number to its bit representation. But here we can see what's actually being used in the systems in order to have efficient circuits, and it's the following. It's to say, instead of executing the kind of bit decomposition in the circuit, I'm going to have this first line with the kind of the hashtag there, where I just set two new variables, C1 and C2, to being the result, right? So it's really easy, like off the circuit, to find a bit representation of a number. And then this is not enough, right? If I just come up with two values, then I could come up with anything, and then I could even put like 5 and 4, which wouldn't make sense. So then the important thing is to then, once I have the result of the computation, I need to have a bunch of constraints that make sure that this result is actually correct. So in this case, if I come up with C1 and C2, which are the bit representation of C, then I need to check 3 things. I need to check that C is actually equal to C1 times 1 plus C2 times 2, right? And that's actually just one constraint. It kind of it works in our current abstraction of just being one constraint to the system. And then I also need to check that C1 and C2 are actually either 0 or 1, right? Because I want to make sure that those are actually bits. So to do that, we use a trick where you just make sure that the square of the number is equal to the number. Because 0 times 0 is 0, 1 times 1 is 1, and there's no other number that satisfies this equation in a prime field. So the kind of general idea is to say, okay, we have this computation, but actually a lot of the times it's way more efficient to do the computation of the circuit and then just verify the computation in the circuit. And that's what we're doing here, where we can do bit decomposition into 3 constraints, and if you have more bits, it actually scales linearly, right? So this is something that was not captured in the R1CS. R1CS just told you that those are the lines, so those are pretty much what R1CS is, but R1CS doesn't give you this, kind of the way to solve the system. And that's something that we also need to carry if we want to interoperate between different systems, right? So from that, we came up with this very simple abstraction where you have basically just two things in circuits. One thing is assertions, and assertions you can think of them as being the exact same thing as R1CS. It's just a bunch of constraints, a bunch of equations that need to hold. And you have solvers, which are ways for someone running the program to find actually which values to set to the variables before they can check the constraints. And those 2 things are necessary so that we can kind of take advantage of all the power of the SHA-256 libsnark implementation. So we kind of took that approach and applied it to SHA-256, and this is what we ended up with. We have basically a ZoKrates function, which is a wrapper around the SHA-256 libsnark. So the way it works is that SHA-256 in our case takes 512 inputs. I have one too many here. So it takes your inputs, and then you have this solver. So nothing happens on the circuit itself, but the solver just takes the whole constraint system for SHA-256 in libsnark and just sets every single variable of the system to what it should be, right? So based on your inputs, it sets all the variables, like all the intermediate variables. There's actually like 27,000 variables. It sets them to some values. And then that's something that's executed in libsnark. So from ZoKrates, we actually do a call to libsnark to say, hey, what's the solution to this big constraint system for those inputs? And libsnark is going to give us an answer. Okay, those are all the values you need to have. But then again, that's not enough. So we need to add all the constraints. And again, those constraints, we can get them from libsnark because libsnark has the whole circuit. And then we can just verify those constraints. And in the end, we just return whatever subset of all the intermediate variables is our actual output. In this case, the 256 bits. So we have this in ZoKrates, and that's kind of first step that we took in this direction. But we actually want to go further to actually have a real way for systems to interoperate. And for the R1CS part, for the constraints part, this is actually really easy because it's just a bunch of constraints. But in this case, when we did our SHA-256 integration, we were still calling from ZoKrates to libsnark to get the witness, to get the solution to the system. And it would be actually great if you could actually get the solution to a system without having libsnark at all. So the idea would be to instead export from libsnark the witness generation, this kind of solver bit, and kind of have that alongside the constraint system so that you could directly import and have the witness generation included. So what we experimented with, so of course the libsnark solvers, which I described earlier. Inside ZoKrates, we also have solvers that are being used inside the language in some cases to kind of resolve the constraint system, and they're written in Rust. And one idea we have is to use WebAssembly in order for all the different tools to compile their solvers, so that then you just need to have a WebAssembly runtime so that you can run the solvers for your system. And that doesn't have any security implications because the whole security of your system relies on the constraints and not on the witness generation. So having something that's really, really portable here makes sense to us. So that's something we're looking at as well. So in terms of the kind of next steps that we're looking at, so having more stuff on interoperability, making it easier for those systems to interoperate, so that we don't have to re-implement SHA in every single toolbox, but instead we can share those implementations. We're also working on a type system. So we have two main reasons why we're working on type systems. So in the current version of ZoKrates, there's only one type, which is the field elements. But this can be very cumbersome for developers to work with, especially if you're talking about a hash function, then you have like 256 outputs. That's not really easy to work with. So the first kind of type that we would want to have is kind of static arrays, so that you can actually in ZoKrates have this array which represent a number of values, and then this gets compiled down to the actual field elements. And there's a second use case where the type system is going to be really interesting is for safety itself. So when you're talking about bits, you always need to make sure that whatever variable represent a bit, so in this case, the C1 and the C2 here, all of this only makes sense if C1 and C2 are 0 or 1. And that's something that we're looking at enforcing in the type system itself, so that if in ZoKrates you allocate a bit, then it's going to automatically make sure that this bit is always 0, 1 all the way through in your program. Finally, integrating with other backends is something we're looking at. So currently we target Ethereum with a specific proof system and a specific curve, but there is no reason why we couldn't just take ZoKrates and target a different curve or a different proof system as long as it's based on the R1CS abstraction. Then just a quick wish list for the ecosystem at large, because we start having people working on those tools and some stuff that we think could be interesting for space. So first, there's this tool called Bellman, which is the library developed by Zcash, which does both kind of circuit generation and also proving. And that's something that is really interesting for us for many reasons. One of them being that it's based on Rust, and we're also building on Rust. Another thing is that they use the concept of streaming the constraints, so that you have actually a reduced memory usage compared to other proving tools. The kind of the drawback of Bellman is that it is developed inside Zcash, so it's very focused on the Zcash use cases. So it only supports one curve, it only supports one proof system. So if we can have Bellman as a kind of community tool that people build on and add more proof systems and more curves, there's already some people interested in adding the Albion curve to Bellman, which would be awesome as well. Then in terms of the curves themselves, embracing BLS 12.381 could be super interesting as well. That's something we're also looking at, but in terms of the support currently, it's pretty restricted to the kind of Zcash community, so it would be great to have more implementation of BLS 12.381, and that's something that the Ethereum Foundation is also interested in. So if you're interested in porting BLS 12.381 to a different language, just reach out. I can help on that. Also, having more developers, because there's so much stuff to do. Like, it's pretty much kind of open territory now. So we have interesting topics if you want to work on those things, and yeah, there's just so much stuff to do. And finally, sharing, I think, is something that's really important, because right now the community kind of benefits of all the great work that the libsnark people have been doing and the Zcash people have been doing on Bellman, but we could use more sharing, like events like today, or the kind of ZCon conference in Montreal, also meetups. So I'm also looking at ways that people can connect more and share their experience with the system, so that we can build best practices and have actual use cases out there. So that's all for me. You can join this afternoon. We have a panel on the use cases themselves, and also definitely check out the tool and come talk to me if you have any kind of disagreement on anything I said. I'm definitely interested to hear your perspective. Thank you.
So I think if there's any questions, I'm going to be running around with the mic. Cool.
Thanks for a great talk. So 2 questions. First, you mentioned the SHA-256. So it's ready now, it can be used? right?
Yeah, we have so we have two implementations. One is ZoKrates native implementation, which is not efficient, and we have a integration with libsnark that you can use. I can kind of show you how to use it. It's not on master yet, but it's available already.
Cool. And second question is, you mentioned the types, which can be Boolean in the future, but now currently you only support the fields. So the operators are also just arithmetic circuits. So I don't have logical operators. Is that correct? So I have to implement logical operators myself with the arithmetical stuff.
At the moment, it's the case, but once we have types, you would definitely have XOR and all those operators.
So can you estimate the ETA for this?
That's something we're working on now. We want to be sure we get it right, but it should be this year.
Okay, thanks.
Okay, all the way back.
Thank you. So my question is on the trusted setup. You said you can make the trusted setup in ZoKrates, but if I set up the trusted setup, it's not really trusted. So could you use the zcash trusted setup for the SHA example?
So that's something that would be really interesting to do. That's something we don't have at the moment. We only have the centralized setup. There are some use cases which work with a centralized setup, especially if you're doing the setup and you're the verifier. So in some cases, it's okay to have this trusted setup. But if you're interested to work on having a more decentralized setup in ZoKrates, that's definitely something we would support. And yeah, definitely.
Any other questions?
Hi, thanks for the talk. Do you have any ideas for ETH Berlin projects, like hackathon-sized projects that we could attempt to do with ZoKrates?
Sure. There is one proposal for a project which is more about ZoKrates itself to integrate ZoKrates with Remix. So that's more on the kind of developer tool side of things. In terms of kind of toy project that you could use, that you could do during a hackathon, yeah, I think you could already use kind of see what you can do with hash functions in general. I know there's some people from Gnosis in the room that also have some very interesting ideas. So maybe kind of connect with them. And also this afternoon we're going to have this panel, so maybe we'll have some ideas after that. Cool.
Hi, thanks for the talk. In the context of verifying Merkle proofs, what needs to be added on ZoKrates to be able to do the verification efficiently? And ideally, if we could do the proof generation for multiple proofs in one, like a recursive setup thing?
Do you mean recursive SNARKs?
I have heard of the name, but I'm not sure if that's what you would want. Ideally, a way to make multiple Merkle proofs of inclusion in one proof.
Okay. I don't see anything that would prevent you from doing that based on a hash function. So you could take a hash function in ZoKrates and then implement a Merkle tree on top of that, and then use that. So I think you could do it today, and we have people who did similar stuff.
Okay.
If there aren't any more questions, we can take okay, we'll give you one more, but then we can take a little break before Howard Wu comes up and talks about DIZK.
Thanks. So in EVM, there is a precompiled contract with this trusted setup based on Zcash trusted setup. Is that correct?
So your trusted setup is not based on the curve, it's based on the circuit. And in this case, each developer comes up with the circuit. So typically, you would do the trusted setup. So whoever sets up the kind of verifier does the trusted setup.
But what about the EVM precompiled contract?
Oh, the precompiled contract is only for the pairing checks.
Okay.
And the pairing checks are used in the process of verifying a proof. But they don't have any trusted setup. It's just
okay.
It's just EC cryptography.
Okay.
Yeah.
Thanks.
Cool, cool. Thanks a lot.
Thank you.
So we're going to be back here in about 15 minutes for our last talk before lunch. See you soon. Yeah. Hello, hello. We have the last session in the main chain stage before lunch, if people want to come and see Howard Wu talk about DIZK. That's not, is it off now? No, it's on again. Do you want to shut the doors? So I think if people are here, we're just going to shut the doors. Henrik, will you be able to help? Henrik, do you mind shutting the doors? Did I? Hello? Oh, sorry. Cool. So I'm really excited to introduce Howard Wu, who's going to be talking about DIZK. We actually got a chance to sit down with Howard, I think 3 weeks ago or so, and do an episode on, well, we were talking about zk-SNARKs, but we did get a chance to touch on this, so I'm definitely excited about this talk. Cool. Take it away.
Thanks. Hi, so I'm Howard, and I'm a researcher at SCIPR Lab in Berkeley and also a partner at Decrypt. Today I'm going to be talking about DIZK, and DIZK is a distributed zero-knowledge proof system. This is joint work actually done with Wenting, Alessandro, Raluca, and Jan. To begin with, you're probably asking, and we've also had a lot of great discussions earlier today on what is a zero-knowledge proof. And I will give you my rendition on this. A zero-knowledge proof involves two parties. You have a prover and a verifier. And both the prover and the verifier know some public function f, as well as a claimed output y. And the prover says, hey, I know x such that f of x is equal to y. You can think of x as your private input in this case. And the verifier wants to be convinced of this, and so he or she will then challenge the prover. They play this interactive game with each other, after which time the prover will convince the verifier if indeed they know this secret. Now, there's one particular type of zero-knowledge proof that has recently gained a significant amount of attention, and this is zk-SNARKs. A zk-SNARK is a zero-knowledge proof with a few additional guarantees. For one, you have non-interactivity. So what this means is that the prover only needs to provide a proof to convince the verifier that they know the private input x. Secondly, you have succinctness. And what this means is that the proof itself is small in size, and the verification time here is fast. Now, one particular type of zk-SNARK that we're going to talk about today, and also is very commonly used in deployment today in industry, is that of preprocessing zk-SNARKs. And a preprocessing zk-SNARK has a function, a setup, that takes as input a public function f, and it produces two outputs. One is a proving key, and the other is a verification key. I try to use size here to show kind of the differences in costs on memory and time, and the proving key here is going to be significantly larger than the verification key. Now, zk-SNARKs in general have many interesting applications, two of which we will discuss today. So the first application that we're going to look at is peer-to-peer payments. And suppose you have Alice and Bob. Alice wants to pay Bob, let's say $1, and she may use a blockchain to facilitate this payment. As you will commonly think, this would actually reveal a lot of information. First off, you learn about the addresses that are involved, and so you learn that Alice is the sender, that Bob is the receiver, and that the payment amount here is for $1. Instead, what you could do is actually encrypt the contents of the payment. And so if you do that, then you could actually get anonymous peer-to-peer payments. But to ensure the validity of the payment, in this case, you would use a zero-knowledge proof, a zk-SNARK, that would be attached with the transaction to ensure that those encrypted contents indeed are valid and justify a proper payment. This is a protocol called ZeroCash, and it's manifested in industry as Zcash. Let's look at a second application. So suppose you want to use a smart contract to run a publicly verifiable computation. We actually just saw in the previous talk with ZoKrates a very nice demonstration of potential use cases and potential directions for zk-SNARKs in terms of Ethereum. And the issue is that today, when you invoke a smart contract, you have to require all the validators to rerun this computation. So a more scalable approach is actually for the caller to run the computation off-chain and instead send along the result along with a proof attesting to the validity of the result. Then the validators would only need to check the proof, which we've established here is cheap. Now, these are only 2 applications of zero-knowledge proofs, and don't be offended if your favorite application wasn't presented here. These 2 applications were actually chosen very specifically to motivate our problem, which I'm now going to address. So we have some good news and some bad news. Well, if we plot the circuit sizes of the applications that we just discussed, we'll see that the private payment application requires about 1 million gates. And this is great. It's actually very practical, and this is why you see things like Zcash in deployment today. Now, if we look at a typical smart contract execution, and we try to map it into the circuit world, we find that the actual cost of these things is around 100 million gates. And for a larger smart contract execution, we find ourselves using billions of gates. So unfortunately, current monolithic zk-SNARK implementations run out of memory at around 10 million gates. And this makes this particular application, smart contract executions, just out of reach from current techniques. So we asked ourselves, what could be a stepping stone for enabling applications such as this? And this is where I present here DIZK. DIZK is a zero-knowledge proof system that is, 1, distributed, meaning it enables the execution of a zk-SNARK setup and prover across a compute cluster. Second, it is scalable, so it reaches heretofore unreachable circuit sizes, up to billions of gates. And the intuition that we have and the pattern that we see is that as we double the number of machines, we effectively support twice the circuit size. The third point is that this is parallel. So it speeds up the time it takes to generate a proof. And again, the pattern that we see is that as we double the number of machines, the general computation itself is roughly twice as fast. So how did we do it? Well, the approach that we took was to take a monolithic zk-SNARK, namely one by Jens Groth from 2016, and distributed it on a cluster of machines. Now, this approach seems quite simple. However, it turns out there were a lot of challenges to distributing the protocol. We chose Groth 16 specifically because it is highly efficient and currently offers the smallest zk-SNARK proof size. And in general, we had to tailor our architecture at every level to ensure that our protocol could adequately demonstrate scalability and parallelism. So let's talk about, and let me walk you through some of these challenges that we face now. So in terms of challenges, let's take this zk-SNARK diagram, and I want to point out that the verifier in this context is extremely small and really cheap to run. Therefore, we turn our attention to the setup and the prover. At first glance, we'd probably want to spin up a cluster of machines and run the setup and prover on it. And next, we'd probably want to use a distributed data structure to represent our public function f, the proving key, and our secret input. This looks all right, however, it's not. And there's several challenges that arise with this current setup. The first is that we're multiplying polynomials of degree that are in the billions. Second, we're representing these polynomials as terabit-sized arrays. Third, we're accessing large pools of shared memory in complex patterns. And fourth, we're synchronizing shared state that incurs significant network delays. All in all, these fundamental challenges are things that we need to overcome, and we do so in the following way. So we start with the setup. And it turns out it's not enough to keep the subcomponents of the setup itself monolithic. And so we distribute the setup by implementing distributed algorithms for the subcomponents of the setup. The distributed setup then outputs a proving key, a distributed proving key, and a small verification key. Just as before, we distribute the prover by distributing the monolithic subcomponents of the prover. And lastly, we will verify that the proof is valid. And again, we forego distributing this step as it's extremely cheap to run. So for time's sake, I want to focus on one critical part of our system, and that's the distributed prover. You will find details of all of this, all of these distributed techniques in the paper for DIZK. It's available online, and I'll show you the link at the end. But today I really want to go over one critical component in this system, and that's namely the witness reduction. So the witness reduction, I will show you some of the off-the-shelf approaches that you can use to compute this reduction. And then I will show you the tailored approach that we use to make this witness reduction both scalable and parallel. So to efficiently compute the zk-SNARK proof, we need the circuit we started with in polynomial form. And namely, the equation that we want to evaluate here is this one. Oops. If you haven't seen this equation before, this is an important equation introduced in GGPR 13 that defines a quadratic arithmetic program which has to do with arithmetization for circuits. And if we zoom in on this equation, there are three terms that need to be efficiently represented and evaluated in order to perform the witness reduction. Also notice that these terms have summations from 0 to n, where n is in the billions. So I'll focus on how we efficiently evaluate these summations. Note that the arithmetic operations outside of these three terms will make use of distributed FFTs, which again you can find it in the paper. And zooming in on one of these terms, we see that there are two components, a matrix A and a vector Z. The matrix A represents one part of the input wires comprising our circuit, and the vector Z is a satisfying assignment for the circuit. You can think of it kind of like a combination of the public inputs and the private inputs that we discussed earlier. So as a straw man for computing this, we might start by representing our matrix A as follows and representing our vector Z as follows. We'll represent these as matrices and vectors in their canonical form, and to evaluate the summation, we need to join the elements by their index I. So as a strawman approach, we may partition our matrix A row-wise and our vector Z element-wise. Next, we'll join our partitions row-wise. So A naught with Z naught, A1 with Z1, dot, 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 down to AN with ZN. And this generates a join table that will look like this. It appears quite uniform in cost, with each entry now independent of all of the other entries. But it turns out that this isn't the case. And let's see why. So here's an example of the data that would be stored in this case. And because of the nature of our circuit representation, our matrix is what we call almost sparse. And this means that most rows and columns are sparse. However, there will always be a handful that are dense. So in this case, think of the red entries as like your dense entries and the green ones as your sparse entries. If we partitioned our matrix column-wise to compute, for the cluster to compute, the second column would be slow and straggle, causing all the other machines to wait on it to finish its task. This is obviously a bad thing, and so this is probably not the best way to look at it. If we tried the other approach of partitioning this matrix row-wise, well, again, we'll actually run into the same problem with the first row as our straggler and causing all of the other machines to wait on it to finish its task. We studied all of the off-the-shelf approaches to address this problem currently, and this is mainly trying to address a problem of data skew, and we benchmarked them across varying circuit sizes and also across varying numbers of machines to determine their feasibility. And the approach that we took with these was to basically say, let's replicate and partition the data so that the computation is distributed evenly. This is what all of the off-the-shelf approaches try to do from it's like a systems level approach. So the first one that we looked at was block join. And block join is one of the common techniques to address data skew. What it does is it will replicate each entry in one distributed data set across every machine. So the hope is that when you're joined with the other distributed data set, the partitions will be more or less evenly spread across the machines. And what we end up with is a join table that looks like this. So at first glance, this table looks quite large, and indeed it is. Block join has performed n+1 times the number of partition replications. And recall that n+1 here is, again, in the billions. And so now every partition here is dense, and therefore the computation is uniform system. And so we turn to other off-the-shelf approaches. Next, we benchmarked another common technique to address data skew that's called skew join. And skew join takes a more fine-grained approach by first computing usage statistics, and it will replicate frequently used entries for every machine. This sounds more reasonable, and indeed in most cases it really is. However, for our system, it turns out this provides us with minimal advantage, and let's see why. So if our matrix A is partitioned row-wise, and we perform a skew join operation with vector z, we see that each partition only needs to access one unique element from the vector z. And in this case, skew join is actually functionally equivalent to the strawman approach we saw earlier. Now, if our matrix A is partitioned column-wise and we perform a skew join with vector z, we see that each partition now needs access to every unique element from the vector z. In this case, we actually find that skew join then is basically equivalent to block join, and that was an approach that we saw earlier that we had deemed to be one that's dense and therefore impractical for our use cases. So no matter how we organize the data here, off-the-shelf approaches will cause unnecessary replications that blow up our memory cost requirements, and it makes it impossible to scale the system. Actually, in fact, I think this approach that we used at the time, it turns out it wouldn't even scale beyond like 50 million constraints on 128 machines. And so until then, this is really it actually turns out to be twice as slow as our tailored approach, and I'm going to describe that next. So for the tailored approach, we implemented one that basically can evaluate our witness reduction and preserve scalability and parallelism. The approach that we took was to isolate and transform the data so that the computation is distributed evenly. And let me show you a high-level picture of how we do this. So we start with the almost sparse matrix A from before, and we perform now a pre-processing step. This will get us our density counts, and so this will get us density counts for each of the partitions that are in this matrix, and these statistics will inform our system how to isolate the dense vectors from the sparse vectors, which we do next. So using this density count information, our system will then split dense vectors into sparse partitions. Now to perform the join operation between matrix A and vector Z, we will perform what we call a hybrid join. A hybrid join will replicate only a handful of the unique elements from vector Z. As we said, our matrix A here is almost sparse. And notice now that in our case, each partition actually just has one dense computation to perform. So our replication factor was minimal, and as our approach is able to preserve the almost sparse structural representation of matrix A, we find that this actually ends up being quite well. This enables us to join our data and compute the summations from before without stragglers. And in practice, for the same number of machines, we find that our tailored approach now enables us to reach billions of gates, where off-the-shelf approaches, we had said, kept us away from being in the billions of gates. And so along with other distributed subcomponents that were described in this paper, we're able to architect a zero-knowledge proof system that is actually scalable and parallel. So we implemented DIZK, and we used a cluster compute framework called Apache Spark. Our system is written in Java with approximately 10,000 lines of code. And we ran our experiments on EC2 using R3-8X large instances. These each have 32 virtual CPUs and 244 gigabytes of memory. Our evaluations showed us some really interesting patterns and properties. So in terms of the largest supported circuit size, well, we first evaluated this and against libsnark. libsnark is a C++ library for zk-SNARKs, and we profiled this in our environment and found that it would reach approximately 4 million gates. When we profiled DIZK across a different number of machines, we found that we were able to reach approximately 2 billion gates with 256 machines. And the pattern that we saw here is that as we double the number of machines, we were able to support twice the circuit size. So this then led us to ask, could we compute up to these large circuit sizes in a time-efficient manner? It's one thing to just be able to reach that. It's another to be able to reach that in a practical manner. And that's where we look at scalability. So here we have two graphs. On the left is the setup, and on the right is the prover. Note that this is a log-log scale graph, and so if we follow the trend on one of these lines, namely the one for 256 machines, we find that the slope is approximately equal to 1. So this is linear, approximately linear. And the pattern that we see is that as we double the circuit size, we're able to support twice the, or we're able to compute, it takes roughly twice the time to compute. And that's a very nice property to have. Here again, we plot the same data now, but show the number of machines on the x-axis and plot the circuit size. So this is trying to demonstrate parallelism. And again, on the left, we have the setup, and on the right, we have the prover. If we follow this line at 2 to the 26, this green line, the pattern that we see here is that as we double the number of machines, this computation is actually approximately twice as fast. Again, this is a terrific property of the system and something that we find very, that would be very necessary for computing large instances. And so in conclusion, we found that that prior zk-SNARKs support maximum circuit sizes in the millions of gates at an amortized cost per gate of 1 millisecond. And we find with our techniques that DIZK is able to support maximum circuit sizes in the billions of gates at an amortized cost per gate of approximately 10 microseconds. The full paper is available on Crypto ePrint. And I'm also proud to say that we've released DIZK as an open source library on GitHub. You can find it by going to DIZK.org. And we've put a lot of hard work into making this library available to the public with a convenient profiling infrastructure so that you can replicate these results. But you can also use it to build new and interesting applications with DIZK. And lastly, I'd like to leave you with 2 open questions. So the first question is with regards to even larger circuits. What techniques will get us to trillions of gates, if any? And based on napkin math, if you look at the current techniques that we use, we need approximately 100,000 machines in the best case scenario, which frankly is too many. The second open question is with regards to other succinct zero-knowledge proofs. So how efficiently can other succinct zero-knowledge proofs be distributed? And you can look at STARKs or bullet proofs. Our techniques are likely an excellent starting point. They share a lot of common primitives below, and it seems to be an area that would be very fruitful to study further. And so with that, I'd like to conclude, and thanks for your attention.
Hello, cool. So here's some questions.
Hi, thank you for the great talk. What is the input for DIZK? So if I wanted to use that, what would I have to pass into it to compile?
Yeah, so to use the system, you basically need to have like a problem, like some function that you're trying to compute, and then you have to map that into a circuit world. Once you have that, you'll have like your public inputs and your private inputs that you need to provide. All of this would then run on either your personal machine or on a cluster machine where you could, it can really be operated on any system that supports the Java, like JVM in this case. And in general, like as long as you have all the dependencies that the library requires you to do, then that's kind of all the pieces that you need.
So it's this R1 CS constraint system, basically, that's the input to the DIZK?
Yeah, so the current library supports like rank 1 constraint systems, and we use that and map it to like quadratic or reduce it to quadratic arithmetic programs. If you'd like to try other approaches, you're also welcome to contribute on that front, but right now that's the MP language that we support. Yeah.
Thank you for the great talk. Looking at the performance graphs, after a certain amount of executors, it looks like the system reaches some kind of diminishing returns. So after, I see that for smaller instances, and after 128, and you go to 256 in the, in this.
1 second.
Yeah.
Animations are slow. They should have like a scroll feature. Okay.
In the next graph, I believe. Yeah, here. I noticed that the setup and the provers in the lower part of the graphs, they start taking longer.
Yeah.
Is there a reason to that? Is it that similar to other parallel, how after a while adding more CPUs does not make the parallelism better and it's just computational overhead?
Yeah, absolutely. That's a really good question. I'm going to move it to this previous graph and just kind of show you on the red curve here. It's the same property that you're pointing out there. The trade-off that's being made is that as you grow the number of machines, you basically start to have this setup cost overhead. And not to be confused with the distributed setup, it's like the actual cost of like turning on and spinning up all of these machines. There is a cost to coordinating all of them, getting them on the same page to solve a problem in this case, to generate a proof. And that cost itself will grow as you increase the number of machines. On this graph, we only plotted from 2 to the 15 onwards, but in practice, because I tried it from like 2 to the 5 and through 2 to the 10, you actually see that it starts to really cross over thresholds, so that to the point that like this will be actually the highest and this will be the lowest. And that's a natural trade-off that you're making, because as you increase the number of machines, the communication costs on network and also memory resources has to be shared, and all of those things grow. And so the real value in this is actually kind of when you start to cross over that threshold and you're looking at large problems, that it becomes useful to do a distributed technique.
Thank you.
Sorry. Although this reduces the cost of calculating a proof from a circuit, is it still prohibitively expensive to calculate the circuit from a virtual machine bytecode or whatever representation that you'd have that would be executable normally?
So are you saying like if I were to have some problem that I map into a circuit and then I want to compute this, like that process before I get to computing would still be hard? Is that the question? Or
I mean like calculating the circuit diagram from some form that a human would write.
Oh, well, so the actual computations here are happening in the cluster, so it would be solved through the system. Maybe I'm not understanding.
I'm not sure I'm phrasing my question correctly. So like, if you, for example, you want to prove some kind of smart contract, is it still prohibitively expensive to use in a real blockchain to have like a human readable language of some kind to compute the circuit diagram from that language or from a bytecode? Is that step still very expensive? Because this this system starts with the circuit diagram.
Yeah, so this system itself assumes that you come to it with like a circuit, right? And the steps leading up to that are not being addressed in the system currently. To make that practical, I would say it's really not too bad of a problem right now. Certainly you have optimizations that would be helpful to basically reduce the circuit size, but from my understanding, and I don't know if Thibaut's here and wants to clarify, but there is basically some cost to constructing those circuits. It's actually a lot less than the arithmetic of the circuits themselves, and so in practice you can do that on a single machine and load it up onto this cluster just fine. It may be an hour or something, I don't know, but in practice like this still remains the bulk of the computations, which it would not be restricted to its bottlenecks on.
That's a great answer, thank you.
Any more questions? Cool.
So these graphs are useful to calculate like times. Like if I have so many machines and so many circuit size, it will take me so much. Is there? Can you refer a like quote a reference where I can actually compare some actual use cases and try to figure out how many, like what's the circuit size? For example, calculate the Ethereum transactions at like so many million gas. Like how much circuit size would I need to construct such a ZK proof?
Yeah, so we didn't evaluate it for like the smart contract case, but we did two applications that you can find in the paper. One was actually implementing another previous paper called photo proof, and what that's doing is think of like Photoshop operations, like image transformations, and each of these image transformations is a state transition. And so if you could have like a proof that the state transition is valid and it only does blah things, and it comes from a logical, like a properly signed like a camera, for example, then you can maintain the certificates that ensure the integrity of the image. So that was one that we did, and we actually were able to get it up to like I think it was like 5 or 7 megapixel photos that on just like 32 or 64 machines, and it would take like a minute or two. It was like pretty quick if I remember correctly. So you could use that as like a heuristic benchmark for like if I had a smart contract and I'm trying to apply some matrix operation. It's a very similar type of context that you could potentially try to map the napkin math cost to. The second application that we did was really like machine learning use cases. So there's a lot of demand for, or interest really for having like verifiably like integratable machine learning computations. A lot of that is just linear algebra really underneath. And so as long as we can represent this in this matrix form, which we actually show it is, then you can compute a lot of machine learning techniques like linear regression and whatnot very naturally in this system, and we also highlight that in the paper as something that's in the realm of practical for small problems.
Any more questions? Oh, one all the way in the back. Hey.
Hey, can you use that approach to do delegation of proofs to a third party? And are there any ways to still guarantee privacy of the private inputs?
That's a really good question, and so that's one of the fundamental trade-offs that are being made here. Like this is a distributed system, not necessarily a decentralized system, and inherently, if you spin up a cluster, the trust model is that I assume that I trust all of these machines to be in my control and to behave honestly with me. So, if I go on AWS and I spin up a cluster of EC2 instances, then I'm assuming here that I own all of those EC2 instances and I'm not tampering that hardware in this case. It's another model to say like, hey, like maybe there's some other party that is doing this. They're spinning up an EC2 instance and I give them my data, in which case like you would need to have like another additional layer of protocols which weren't explored here, but I would think like you could do some type of encryption approaches or homomorphic encryption approaches that, while extremely costly, may get you something okay for reasonably sized problems. But that's an area that's certainly open for more exploration.
Thanks.
Mm-hmm.
Anyone else? I don't know if you can tell, but lunch is actually, I think it's been served. So thank you so much, Howard.
Thank you.
And you guys, we'll be back here, I think, at 2. I think that's when it